Good morning, everybody. Today's Codeforces Round 683. I'll be competing today, and it's a div1, so it's rated for me. So that'll be kind of fun. As usual, solutions to everything I know how to solve, and also the div2 only problems, will be at the end of the video. And good luck, have fun to everyone competing. I really need a haircut, don't I? Well, I'll sort that out eventually. Yeah, anything new about the writers? I'm not familiar with really any of them. Although Devil, I guess he's pretty common. Alright, we've got our template. Should be ready to go. Commentary is also going to be on the lighter side, because it's rated for me, obviously. Yeah, okay. Okay. Otherwise, plus equals the weight. All right, and then anything else? Yeah. This should be out, not system.out. And then this should be out.print I plus this, or I dot ID plus a space. Seven. 1, 2, 3, 4, 5, 6, 7. If wait. Yeah, it seems fine. All right, on to B. We'll listen for our result. Got it. Oops. Two strings C and D is their similarity score. 4 times the longest common subsequence minus the 2 lengths. So this is the whole thing. This is ABA, right? Yeah, let's do this example out on paper. We've got A, B, B, A, and then probably ABA. That's what they're going to ask for. So this is 3. So it's 4 times 3 minus 7. Which is 5. So if we add one character to both, this will give us a +2. If we add an A and a B, this will give us a -2. All right, but that's not a helpful transition. I think we just want to add an A. That'll be a -1. Or add a B. That'll be a -1. Can we do an n² dp? So you can stop here for both. You can continue top. You can continue bottom. Or you can continue both. That should be fine. If that's the solution, I think it should have some solves by now. It's got 21 solves. I think that's reasonable to try then. Time limit 1 second. I might make this iterative. Or it doesn't go that deep. Only goes 1,000 deep, so maybe not. Maybe I'll just call it iteratively. They have to be non-empty. Yeah, presumably that's fine. I guess let's just make this I, make this J. Yeah. That's an easier way of handling this. Alright, and then best equals math.max, best, 2 plus go, I plus 1, j plus 1, if a at I equals b at j. B length equals this. Alright, and now d key, new int array a length by b length. Fill that with negative ones. Oh, we need build back? No, we don't need build back. convenient. Okay. For int I equals a length minus 1 greater than or equal to 0 minus minus. Array index out of bounds. Why would that be? Alright, this sounds like a really boring problem that I don't like at all. But I think it's fine. Yeah, usually I'm pretty optimistic about problems. This one I think was just boring. Like, that was super unoriginal. It was basically the same thing as LCA. I didn't like it. Didn't feel good to solve or anything. Anyway, on to the next one. For a given sequence of distinct non-negative integers, we determine if it's good in the following way. Consider a graph of k nodes written from B1 to Bk on them. For every I from 1 to k, find a j such that Bi XOR Bj is the smallest among all such j, where XOR, yeah, okay. For each I from 1 to k. So we've got some distinct integers. We want to see if it's good. We make a graph of all these things. Okay, now for each I, find one j with the smallest XOR. Draw an undirected edge between those vertices in the graph. Say the sequence is good if the resulting graph forms a tree. Oh, okay, don't, wait. Shouldn't it have k edges? Oh, is it? So 0 goes with 1, 1 also goes with 0, so you've got like a duplicate edge here. Yeah, that makes sense. Right, so yeah, so we need to figure out properties of this particular tree. Speedy, quick. If you have, what's the output? The maximum size, the number of possible elements to remove. Yeah, so You can't have any two things with the same bit on. The same highest bit. The answer is going to be at most 30 or so. Yeah, if you have two different elements with the same highest bit, the answer is going to be no. Because you'll have this 6, 5 thing, because they both share a 4. Do we just care about... So if there's a unique highest bit for everyone, is that all we're interested in? Might be. Yeah. So let's try this example. 6 is 1, 1, 0. 9 is 1, 0, 0, 1. 8 is 1, 0, 0, 0. 7 is 1, 1, 1. 3 is 1, 1. 2 is 1, 0. 5 is 1, 0, 1. Oh, okay. So, oh yeah, we also get to keep one pair that are the same, that have the same highest 1 bit. That's fine. So these two collide. These two collide. These 3 collide, and these 2 collide. Yeah, 6, 7, 5, 3, 2. So how do we do this? Oh, we keep the biggest group, maybe? That might be a wrong submit. Is it worth trying? 1, 0 would go to 1, 1. 1, 1 would go to 1, 0. Yeah, so it's not just purely based on the highest 1 bit. So if you have a try, this is a 0. This is a 0 as well. This can be a 1 or a 0. So you find the closest thing above you. In this try that matches something else, that's what you draw your edge to. If you ever have some node that has 2 plus kids in its left and 2 plus kids in its right, you're in trouble. Because they'll never join. So you need to make one of them 1, and then continue in the other half. Yeah, okay. bit is equal to 0 n times here plus plus. Guess this will just be subtree size. It's always just subtree size. Okay. Bit's not equal to 0. Then if I and one off shift bit not equal to 0, Alright, so then kids val.insert I bit minus 1. So that we can build our try here. Okay, so go, we need to pass in the number of skips. Well, I guess, what is this? This returns the max kept. We'll just do that. Alright, so if size of kids at 0 is greater than 1. Well, okay, so this is keep left. So if size at kids at 0 static kids at 1 go kids at 0. Okay, add equals math dot min 1 size of me dot kids at 1 or at 0, and then best equals math dot max of the best, and add plus go of me dot kids at 1. Yeah, so that's fine. So this gives us everything we need. Turn dp at, well, no, just return best, because we call each thing only once. Okay, and now don't believe it. Why is my code wrong? Okay, so 6 is 1, 1, 4, and 1, 2, and then 0, 1s. So this is 6, 5 is 1, 0, 1. That's a 5. Okay, so we're going to have to delete one of those. Then we have this 0, followed by a 0, followed by a 0, that's 0, followed by a 1 is a 1, followed by a 1, followed by a 0, that's 2. Oh yeah, so if depth is equal to 0, return subtree size. Yeah, I think that's fine. Let's runtime analysis real quick. We only get down each of these once. We should only hit this once. Submit, C, good. A little close on the time limit, I'd say. But probably not the end of the world. 86th place. Oh man! CF predictor is so fast. Wow. Nice job, whoever writes that. That was very quick. Alright, so this is a very tricky position that I've finagled myself into. What do I do here? Okay, so testers think it's easier to solve both of these than it is to solve either of these problems. Yeah. Who? Yeah. It sounds like, well, I'll just read D1 and D2 and then think about what to do from there. I think that sounds like a fair idea. It's the easy version of the problem. It's different by the constraints on the array elements. Given some array, your goal is to find the length of the longest subarray such that the most frequent value is not unique. In other words, there should be at least 2 values that occur the most frequent number of times. What is a subarray? It's like every question. We need better definitions for this because every time. Subarray, substring, subsequence, it's just like every time we need a definition for it. An array C is a subarray of array D if C can be obtained by deleting some elements from the beginning and the end. So contiguous. Only 100 elements. Is that the thing with D2? Does not have only 100 elements? Yeah. I mentioned in a blog entry. Hang on, quick break. That's a good answer. All right. I think I understand the problem. Can we binary search the number of times? Whatever it is we're binary searching for doesn't have a real meaning here. It's also not binary searchable. Well, maybe it's binary searchable if you get the parity right. well, we could brute force which element is the most frequent and also where it starts. Maybe do some sweep. Interesting. Yeah, so maybe we'll try brute force which element. In the pair. So if we know like all the positions of the interesting elements that we're considering, we need the max occurrences of everything else. So when does each number pass? Yeah, okay, so this is like a +1, +1, +1, +1. So we're interested in zeros here. Is it always the most frequent element in the array? That's an interesting question. I wonder if it is. I wonder if you always keep the most frequent element in the array as it is. So 1, 1, 1, 5, 4, 1, 3, 1, 2, 2. Yes, you just keep the suffix here because you've got your 2 1s and the 2 2s. You only ever have one problem. Your problem is that you have too many of some number. You need to get rid of enough instances of that number that you can reach some other number. So that means the last, if you delete from the left or right, the last thing you delete will be one of that number. If it was one of something else, there's no reason to delete it. Yes, so we know what the most common element, we know one of the most common elements. Got it. Yes. So now for some other element, well, we could brute force what the other one is, even. That gives us a bunch of yeah, we brute force one, I guess, yeah, brute force what the other element is. The only problem we would create is having too many of some other element. But that would be solved easily, so we don't need to worry about that. So now we have a bunch of A's and B's. We want to find the longest, oh, they're coordinate compressed A's and B's too. And in linear time, we want to find the longest range of these things that have the same number of A's and B's. Yeah, okay. All right, so let's iron out the solution details. So it's the most frequent element. We need that. Because that's going to be part of the answer. Then we need the number of times everything occurs, or the positions everything occurs in. Yeah, the positions everything occurs in. Well, that's fine. We'll worry about that later. So now we brute force the other element. Now we need to pick some substring that's the same. Yeah. Max substring with the same number of A's and B's. Okay. We can do that for sure. I don't know if this will extrapolate, but we'll think about that in a minute. So int most frequent equals 0. If occurrences of at I size greater than occurrences of at the most frequent size, then most frequent equals I. Then so if there's only one value, yeah, it's got to occur 0 times. Okay. Well, we'll try that. So let's just base case that. Okay. Should be fine actually. So yeah. So if occurrences of other is equal to most frequent, and continue. We need to know the earliest time we saw it. Yeah, okay, that's fine. So we've got all of these positions. We also need each of the characters. Oh, I think I might see how to speed this up a bit. It's gonna be ugly though. All right. Positions will be little things. dot size. The reason I'm doing this is because array lists are slow in Java, and I think this is going to be a little tight on time. I don't want to get stupid DLUs. Okay, so then, because I'm going to be using whatever the big one is a lot, like 10 to the 7 times. Or 2 times 10 to the 7 or something. Alright, so while p1 is less than p1's dot length, or p2 is less than p2 dot p2's, if p1 equals p1's dot length, then deltas at p1 plus p2 equals -1, positions at p1 plus p2 equals p2's at p2, p2 plus plus. Anything else? I think that's all. Continue. P2 is equal to p2's dot length, then we increment p1 and assign a p1 here. Make this a 1. Okay, otherwise, if p1's at or p2 or p2 is not equal to p2's dot length, and p2's at p2 is less than p1's at p1. Okay, this is really just an else then. So now we've got everything here. Best equals math.max is best, and go with these positions and these deltas. All right. So what do we need? The last time the prefix sum was each value. Yeah, okay. prefix sum equals 0. Enter a last time saw, or first time saw. Alright, so we've got the min, the max, and the prefix sum. The min, max, yeah, so this is going to be max prefix sum minus min prefix sum plus 1. Let's just do plus 10, because who cares? Yeah, okay. Now, arrays.fill, first time saw with a big number. Okay, cool. So now for into I equals 0 less than n plus plus. First time saw prefix sum 0 is math.min first too long. Okay, so this is less than n equals, well, I is less than positions dot length. So we can choose not to include this if we'd like. So what does this actually look like here? We're gonna always want to go we're gonna end right before something that we don't want to include. Yeah. So we end right before something, and we start right before something as well, or in the beginning, or the end. Okay, so int end x will be positions at I. And then the start x will be, yeah, inclusive. First at prefix sum, positions at I minus 1. This will be the first prefix sum. First time it was this. Yeah, we'll just have to set this appropriately later. Best equals math.max of best, along with subarray, yeah. The best and end x minus start x plus 1. All right. So after this, last x will be positions at I plus 1. and then first at prefix sum, well, prefix sum plus equals the delta. And first at prefix sum is math.min, first at prefix sum, or last x. Yeah, okay. We also need n, right? Yeah. So end x will be n minus 1. And start x will be first at the prefix sum. Best equals math.max with best end x minus start x plus 1. All right, chances this is right. Null pointer exception. Right next to the bounds. -1. Oh yeah, darn it. So this first needs to be this everywhere. I say 8, huh? Oh, that's a problem. Why would I say 8? Okay, well, let's try this. So positions and deltas, and then yeah, okay. So we'll set the max value equal to 5. Zero, 1, 2, 5, 6, 7, 8, 9. So that's right. 1, 2, 3, 4, 5, 6, 7, 8. Should be these 4. Should be 3, to 9. First 0. What? Seems not right. First time the sum was 0. 0. First time it's 1 was not 0. Okay. Last x is initially 0. What is this last x even used for? Yeah, okay, this is really positions at I plus 1. All right. Ugh. Yeah, I think that's fine. Oh, nope. Thank you. Let's see. Got it. How many pretests? 24. Not bad. Not bad. All right, let's try. Well, let's see. What are the IGMs doing? Let's follow in their footsteps. Following in the footsteps of Ben Q. Yeah. Well, it's good for them. Oh, should I read it? Oh, it's so tempting. This took him 20 minutes. This took him 40 minutes. Andrew hasn't even gotten D2. Raid Wish and Case on half. Alright, maybe let's not look at my friends. Let's just look at the world. It's a bit more compelling to work on D2 instead. Yeah, okay. I'm going to take a quick break, and then I'll be right back. All right, let's understand what we're doing here, how we can speed it up. Thought this would be easy to speed up, but actually it might be super hard. Well, okay, so yeah, what I was thinking about doesn't work obviously, but we can do this better. Yeah, we can still do this. Yeah, we should be able to get this, I think. The idea is that we'll do it for everyone at once. So yeah, that's our contest. We know how to do D2, so we'll spend the last hour doing D2. And then just not worry about these last two problems, regardless of how easy or hard they are. It's geometry though. I want to do it. We have an integer k with n distinct points on integer coordinates. Consider all squared pairs of points. We want to find the kth smallest among these distances. Oh my goodness, bro. Yeah, it sounds like a binary search and a sweep. Binary search of circles, sweep left to right. Then you're doing a range update for a range of circles. This isn't that bad, to be honest. It's actually just not that hard. Oh, maybe this circle part is hard because they intersect, so you gotta do that in a good way. It's also Delaunay bounds. Yeah, I don't know. We know how to do D2. So what we're gonna do for that is, I think it makes sense to try everything at once. we have the most common thing in some places. Every time we see one of these, we need to decrease the prefix sum. Decrease everyone's prefix sum. And then we also need to mark this is a first for everyone. Decreasing the prefix sum is easy enough. Marking as first is tricky, because it's different for a bunch of people, and then we propagate it to different people differently. So that part is hard to do. So is there a better way of doing it than that? We can't just compress the thing that occurs a bunch and keep using this, because like it's not gonna work. Yeah, it's not right. Okay, we don't know how to do this problem. Let's do another check of solves. This is 10, this is 3. And I'm a geometry man, so this is kind of right up my alley. Oh, the distance from the points, from the pairs of points to the origin. Got it. It's a very different problem. That would explain it, because you can't just do distance squared easily. Oh man, good luck, bro. This guy only does the hardest ones first, which I guess is going to be challenging recently. Alright. Yeah, I think maybe D2 is the way to go. Should I go for hacks? Are there any hacks? Is there even anything hackable about any of these problems? Interesting. Yeah, I'm not sure. I'm gonna take another short walk, see if I think of anything. I realize this video is going to be incredibly boring, but sorry, that's not the priority here. Priority here is to do well in the contest. regret to inform you that my stroll was remarkably unsuccessful, and I have come up with no new ideas. We want to make this runtime not depend on the size of this first array. We can make it only dependent on the size of the second array, the smaller one. That'll be fine, because then the runtime will be linear again. Or if we can make it like dependent on the first array times a log or something, or like log of the first array size. That might also squeak by. Yeah. Challenge is, how on earth do you do that? It's kind of unfortunate. Looks like no IGM for me today. Yeah. Unless I can get this problem. Or maybe, I don't know, should I go for F? Oops. Is this a parallel binary search? That's very tricky to do, though. Yeah, that's tough. It's a cool problem. I don't know how to approach it. This is also a cool problem. Don't know how to approach it again. Common theme. I think the solution is to just be very smart. Oh, wait, we can skip some of these. That'll make it n root n. Yeah. Okay. So in order for... Oh, man. Okay, I can get an n root n out of this, I think. $200,000 with the 1.5. Oh, it's gonna be so tight. It's already tight. What was my submission? What was the time for that even? Okay, never mind. It's not tight at all. Yeah, we can probably squeeze a log factor on top of that too and be fine still. Oof, this is gonna be, ugh, yikes. Okay, so if you ever have a run of more than size of A, then it's like greater than or equal to 2 times the size of A, then we can make it just size of A. We can like ignore some of those things. Which makes the total size will be less than or equal to size of A times 2 times the size of A, which is very messy, but what we're looking for. Yeah, so that'll clean it up. It's an n. Ooh, what is it? It's n root n. N root n plus n log n. Should be fine. All right. So this part can all stay the same, actually, which is nice. We just need to build it in a better way. Dare we use a tree set? I think we dare. Yeah, okay. So, well, what's the idea first? Let's solidify that. In order to build this group, we need, like, we have this k equals the size of the smaller. We can actually trim this later if we TLE. We can trim that. But let's not worry about that for a bit. We need all of the smaller things. And also all things within k, like bigger units of a smaller unit. So this part's going to be the hard part. Okay, so do we want a tree set of these most frequent things so we can remove them? It's a lot of tree set removes. Yeah, we can't have a tree set. Yeah, okay. Let's actually bring this code back. This is dot size. Okay, good. Oh, this is a big one. All right, so we've got this part done. So now we just need to build this thing. Last index taken equals -1. K equals P2 blank. Yeah, okay, so now I need to binary search for the interesting, or for, yeah, what are we looking for? For the last index less than I. Static int yes from array A x turns the index of the last thing less than x. Or nothing's less than x returns -1. Yeah, okay, let's try this. Where's the index of the first thing greater than x? Okay. So P1 index will be binary search for, in the big occurrences of I. Next take equals math.max. Next take P1 index minus K. Less than or equal to P1 index plus K. Then big occurrences to use dot add big occurrences at next take plus plus. I think this is actually fine. Oh, we just need this. Okay, this is easy. Int min equals 0. Max equals length minus 1. Return min probably. Int mid. If A at mid is greater than X, then max equals mid. Else, if it's less than X, min equals mid plus 1. Min equals math.min, min and A dot length minus 1. Just to be safe, Should be fine there. So we binary search a linear number of times total with this. Then whatever k is, we edit most that many things. Yeah. What? What? How? Oh, do I need one more? Should be right at the very least. Come on. What? That's kind of wacky. Hello? It's just empty. Oh, ooh, that's a problem. I see. Okay. Yeah, so I do have to modify this a bit. Because it's a good thing I caught that. And I need to only include ranges. That's tricky. Okay, so what do I need to do here? I need to only include ranges that have at least 1 + 1 in them. So I can't include just like an empty range here. We'll make a versioning array. This is getting messy. This is, that's not the right way of doing it. Let's do it right. How much time do we have? We got 20 minutes. Yeah, let's make a version array, I guess. Oof. Alright, fine. Version. This thing goes -1. Version at this thing. It's not equal to I-1. Then we can take it. Version at this equals I. conversion this is not equal to this minus 1. We can take it. It's not even close to right. Oh wait, this should be this. That's even worse. Oh, this needs to change. Yeah. So that's fine. That's 6. Okay, that's good. This needs to be fixed. So let's try adding just a massive amount of 3s to this case to see if we're actually trimming it down at all. Should be fine. Yeah. So let's try this. little nervous on time, to be honest. So fast. It's very fast. We'll see if that passes system tests. And that's my contest, folks. That was a really cool problem. I feel very good about solving that. Unlike problem B, which was just kind of lame, that was really cool. Is this hackable? I don't know. I hope pretests were strong. It would be kind of a jerky move on them to not make it like that. Looks like they're decent. Alright, well, today is my lucky day. If I pass system tests, I'll be very excited. If I get plus 153, yeah, that'll be IGM, right? I can't do math, but I think I can get IGM. We'll see, we'll see. That'd be pretty cool. Yeah. There are no hacks, so I'm not gonna spend time doing that. Because like, I don't know. I don't enjoy that part of the Codeforces like experience. I like solving problems. I don't like figuring out why other people are wrong, like reading other people's code. And like ultimately, I do programming contests because they're fun, and I train in order to get better for like ICPC stuff. That's like the alternative benefit. And hacking doesn't help me with either of those, really. I mean, like maybe tangentially it helps me debug my teammates' code, but like, I don't know. Instead, I'm gonna read the div2 problems so I can talk about them. Man, I am surprised how speedy that was. Anyway. What are my friends doing? My friends are... Oh, I asked Liz Trader. Thank you for waking up, Liz. That's good. Other than that, yeah, no one else is really, like, up, which is kind of disappointing. But oh well. Let's read these problems. Add candies. You have a bag of n candies. Initially, the ith bag contains I candies. You want all bags to contain an equal amount of candies in the end. To achieve this, you will choose an m up to 1,000 to perform m operations. In the jth operation, you will pick one bag and add j candies to all bags other than the chosen one. You want to find a sequence of candies after which all bags will contain an equal amount of candies. Can be proven for the given constraints. This always exists. You don't have to minimize m. So you can pick like 1, 2, 3, 4, 5, 6, then 6, 5, 4, 3, 2, 1. Then that'll work. So that's the idea for that. Cool. Given a rectangular grid with n rows and m columns, the cell located in the ith row from the top, jth column from the left, has some value written on it. You can perform the following operations any number of times. Choose two adjacent cells. Multiply the values in them by -1. Two cells are adjacent if they share a side. Note you can use a cell more than once in different operations. You're interested in x, the sum of all numbers in the grid. What's the maximum sum you can achieve with all of these operations? Yeah, so, well, this is kind of interesting, but I can talk about that. All right, let's talk about solutions. So this is going to be just solutions to all of the div2 problems, and that's it. And I guess the div1 will share C through F2. I'll just talk about them from a div2 perspective. As soon as I find my pen. All right, sounds good. So let's go. Problem A. Okay, so you've got some candies. You want to give the same amount of candies to a bunch of people, but you have these constraints of how you have to add them. So one thing you can do is, let's say we've got the bags like 1, 2, 3, 4, 5. We can add, so we'll add 1 candy to each of these things. But instead, what we'll do is we'll imagine we add 1 candy to everything, and then we like subtract 1 from this. So we'll think about like the candies that we've removed instead of the candies we've added, because that conceptually makes it easier. So we're missing this candy here. The next time, we're going to be missing 2 candies from someone else. So I'll choose to miss 2 candies from this second. These will be like negative candies, I guess, these blue ones. This will be missing 2 candies. Then this one will be missing 3. This will be missing 4. And this will be missing 5. So yeah, we've got that. Okay, very cool. Now we can take some more turns and we can subtract 6 from this right column. So we can 2, 3, 4, 5, 6. 5 is way too many. Okay, let's just say we have 3. Yeah, okay. So on the next turn, we have to subtract 4 candies from someone. So we'll subtract 4 candies here. Then we subtract 5. Then we subtract 6. And we've now subtracted the same number from every person. We've also given them a whole bunch of candies too, but these are like the ones we've like taken away after we give everyone the same amount of candies. So this is like a common idea. One thing you can use this idea for, like knowing this, is figuring out n choose 2, if you want to calculate n choose 2 quickly. So n choose 2, if you have like n elements, is the number of ways to pick 2 elements from the set. Well, if you've got 4 elements, you can match this one with 3 other elements, so it's 3. This one you can match with 2 other elements to its right, so 3 plus 2. This is like plus 1. But in general, you could have like a lot of these numbers, right? So you could have like 1 plus 2 plus 3 plus 4 plus 5 plus 6 maybe. And you can pair these numbers up and notice these pairs all sum to the same thing. In this case, they all sum to 7. 1 plus 6 is 7, 2 and 5 is 7, 3 and 4 is 7. So you can calculate the sum really quickly by using that. And that's like a common trick. I think that's how Gauss got his recess back, if I remember the stories correctly. All right, so that's problem A. Pretty easy. Problem B, numbers in a box, or number box. Yeah. So you have some grid with some numbers. Let's use this example, I guess. 0, minus 1, minus 2, or minus 1. What did they choose? Yeah, okay. Minus 2, minus 2, minus 2. Minus 3, minus 3, minus 3, minus 3. Minus 4, minus 4. Minus 4, minus 5, minus 5, and minus 6. So now what you can do is switch the sign of 2 adjacent numbers like this. So you can swap, you can like make both of these positive or both of these negative. That's the idea. And yeah, that's what you can do. So here's the observation here. Let's say we have some grid that's mostly full except for like 2 numbers in it. Or it's mostly all positive except for 2 numbers. So suppose like this number is negative here, and this number is also negative. What we can do is flip the sign on these 2, then on these 2, and then on these 2. After we've done this, we've got like some chain, right? In this chain, all of the numbers except for the first and the last one, will be flipped twice. So this number doesn't actually change. Any of these don't actually change, but these first and last thing in the chain do change. Which means if we're allowed to do this operation as many times as we'd like, yeah, you can use the cell more than once in different operations, and you can perform the following operation as many times as you'd like. What you can do is pick any two numbers anywhere in the grid and flip both of them. So basically, if you have two positive or two negative numbers, you can make both of them positive. If you have a positive and a negative, you can switch which one's negative. So what that means is, first you want to count how many of your numbers are negative, right? So like count your negatives. If you have an even number of them, you can make all of them positive, and then you're fine. So then it's just the sum of the absolute values of all numbers. Otherwise, whatever number has the smallest absolute value, that is going to have to be negative, because you have to put your odd negative sign on someone. So you put that odd negative sign on whatever thing is going to hurt you the least, and everyone else is positive and contributes to your sum. That's the idea. All right, cool. Problem C, knapsack. So yeah, so I'm pretty sure my solution to this is right, but the general idea is you need to run knapsack, except you have this very wide window of what you're allowed to hit, and you just have to find some subset of items that come close to that window. That's the idea. So whether it's possible is actually like about as difficult for me, I think, usually, as determining what that set is. But we'll just start with determining what the set is, and that'll be proof for when it's possible and when it's not. A good way of thinking about this is imagining we have like some big bar here. So we've got this full knapsack that we want to fill, and we've got this like cut point in the middle here. So there are a couple of types of items that we might consider. The first type is some item that's bigger than the entire knapsack. Obviously, we don't want to take that because like it's too big for us. So we'll ignore all of those items, easy enough. And the next type of item is items that are in this bigger half. So items that are over half of the weight of our knapsack. These items are tricky because if we have these items, we might like not be able to take it, even though we still don't have enough room. So we want to special case these items. But what's nice about them, though, is we can instantly win if we have at least one of these items. So if we have any of these dangerous items that that we can't take as long as we're not full, if we have any of them, then we can just take that item and win. So that's the idea. So we've got any of these big items, we can take them if we want to. In the other case, all we have left is these small items. Okay, if we have small things, we can just keep taking all of the small things we want until we can't take anymore. But we know since all of these items are smaller than half of our size, we can fit all of, like if we fit as many as we want, if we can't take the next items, then we're going to be almost full. So we'll be like over halfway full. That's the idea. Yeah, you can probably prove it by saying like you have two sets, right? One of these sets is going to be half the size. That's probably what the editorial proof is going to be, some kind of math heavy thing. But the code for it looks like this. You've got a bunch of these things, you read in the weight, and then my item class just has its ID and its weight because you have to print the ID at the end. You can just use a pair if you use C++. And if the weight is bigger than the weight of my knapsack, you skip it. If you can win with just this, then you store that as like your winning way. Otherwise, you consider winning by adding this as a small item. Then at the end, if you have one big item that you can win with, you win with it. Otherwise, if you have enough small items to give you enough weight that you're across the border, then you use those. Otherwise, you're going to lose. So that's problem A, or C, I guess. Problem D, or B for div1, is a super boring problem. If you know longest common subsequence, it's basically the same thing, except they have a slight modification. So it's 4 times, the amount you're trying to target is 4 times longest common subsequence, minus the length of the 2 strings. If we just think about this for a minute, like literally it just takes 1 minute, we've got some longest common subsequence we're going to build, right? So let's say it's like A, B, and this one's also A, B. If we add another character here, well, then we get, we've added 1 to our longest common subsequence, so that's like a +4, but we lose 1 for this length, and we lose 1 for this length. So the total of adding like 1 more character to the longest common subsequence is +2. Adding 1 character to either of the substrings costs you -1. So that's the idea. You just run longest common substring as the normal DP. So the state is you're doing some DP where you have the index in the top, or index like in A, and then you also store your index in B. And then you have a couple of transitions. Your transitions can be, you can like take from A only. You can take from B only. If the 2 characters are the same in these 2 strings, then you can take from both. So you can increment both pointers. Or you can choose to end here. You can end your substring here. So in code, this is my DP method. And I want to solve for if I have the suffix starting at I and the suffix starting at J. Suffix starting at I in string A, suffix starting at J in string B. And I'm going to brute force what my starting points are. So that'll be fine. I do that up here in the DP, and then I just print whatever's best. But anyway, I'm doing this part here. If one of the strings is empty, the answer is going to be 0. Otherwise, there are a couple choices. Either I can extend one of the 2 characters. I have to pay 1 for that because I'm using a letter I don't use, so it costs 1. And if I want to, and these are both the same character, I can optionally choose to take both of them. I'm pretty sure you'd always take this, but it doesn't matter. Like having these worst choices, they'll just get ignored. But you can increase this, you can like use this letter in the longest common subsequence. That'll give you a bonus of +2 instead of a cost of minus whatever. And you have to increment both pointers for your next DP state. So that's the idea for the DP. It's literally that simple. And you just find the best answer and print it. So yeah, that's it. Okay, next problem. Oh wait, were we at the next problem? Catching cheaters? No. This is the next one, XOR tree. Okay, so yeah, this one was a little bit tricky. I didn't see it coming at first, so it's like, I guess understandable if, I guess you go down a wrong solution path or whatever, because there are a bunch of things you might think, but it's kind of tricky. What we're gonna look at for this problem, let's talk about the problem first. So you have a bunch of numbers in just like some array of numbers they give you. And what you're going to do is for each number, you're gonna have 1 outgoing edge from that number, and you'll take that number and you'll put the outgoing edge to the other number in the group with the smallest XOR between the pair. So in this case, let's look at the 5. The thing in this group with the smallest XOR for the 5 is the 6, because 5 XOR 6 is 1, 5 XOR 0 is 5, 5 XOR 1 is 4, 5 XOR 2 is 7. So 5 and 6 give you 1, which is the smallest of those numbers that I listed. So that's why the edge from 5 goes to 6. Same thing, the smallest edge from 6, you could do this again, goes to 5. So these 2 edges get added twice, and that's why this there's only 1 edge here. Now, I think you'll never have cycles in this graph, but I think that's also probably not super important. Yeah, it's probably not super important. One thing you could do is count the number of edges in the graph, but for me that was a little tricky. The easier way was if you think about all of these numbers in binary, we'll write them out. So 0 is just 0, 0, 0. 1 is this, 2 is this, and we have 5 and 6. We're gonna have these binary numbers. We'll insert them into a trie. So that's a common trick with XOR. We'll make this big trie here. And I'll draw the edges in a different color so it looks pretty. All right, so as usual, this is going to be a 0, this will be a 1. Now we'll insert these into the try. So we've got one thing here, we've got one thing here, and this is a 2, this is a 5, and this is a 6. Now here's the important thing to notice. When we're at this node here, or if you have, let's try it again. If we want the smallest thing that XORs with this, really what that's going to be is the thing with the lowest, lowest common ancestor. We want the minimum lowest common ancestor with any other node. The reason for that is if you go down the same path for two different numbers, when you look at the XOR, that won't be a 1-bit there. It'll be a 0-bit. And these first bits are the most important ones because this represents a 4, and this represents a 2, this represents a 1. So the 4 is like the most important thing that you want to minimize. If you go down the same path for two things, then their XOR will be smaller. So since we started with this most significant bit, the smallest thing, the thing this is going to have an edge to basically, is going to be this item here. Now, we want to remove some of these nodes. The problem is, I guess, remove the fewest number of nodes so that it does form a tree. The problem we have here is if we have 2 elements over here and we have greater than or equal to 2 elements over here, we've caused a big problem for ourselves. These parts of the tree won't be connected, and we have nodes in both parts of them. So I guess that's the issue. What that means is we have to delete all but one element in this subtree. That way this element will be forced to come to the other side. Or we have to do the same thing for the other subtree. We'll just try both of them and take whichever one's better. That'll be linear time. So ultimately, the solution that we'll find is the best is we delete one of the 2 from this subtree. We don't care which one it is, which ones it are, which ones it are. We don't care which nodes we delete, which nodes are deleted. But we want to make sure only one is left here. So we'll have the 1 here, and then whatever the best answer we can get for this subtree. That's the final answer. So we'll have a +1 here. Then in this subtree, we'll try both of these. It'll turn out the best way is to use, well, actually, we don't have to delete anything at all because we can keep the one thing in this subtree here, and this has 2. So we're fine with having 1 in this subtree because it's forced to have an edge here. And this has 2, and then there's only not much up here, so that'll be forced to come down, I guess. Yeah, that should be fine. Yeah, we know we have this edge here because it'll be coming down from the node here because there's only one in this subtree. So that's fine. All right, what was I saying? Yeah, we have 2 nodes in this subtree, so we'll use both of these, and these will connect to each other. The order doesn't matter. It'll be like mutual, I guess. And then we know we'll have this edge because there's only one thing here, and then we know we have this edge. So I guess in addition to having this tree that we make on the numbers, we also kind of have a tree on this try. There's some spanning tree that we select. And we only get that spanning tree from LCA paths to the closest thing with your lowest LCA. If we follow this constraint that both the left and the right kid have fewer, one of them has fewer than 2 nodes in it. So yeah, okay, that's the idea. Making that a little bit clearer might be helpful, so we can look at the code for how it works. It's actually really simple to code, so I can understand how some of the LGMs are able to get it in just a couple minutes. But the idea is, first we insert everything into a try. So for every element here, we insert it into the try. My try just has, it's a try node, it's got a left kid and a right kid. So if whatever bit I'm interested in, if this isn't the bottom of the try, then I need to insert this to the next person. And the value is if this bit is, if it's not a 0, then I'll look at the right kid, otherwise I'll look at the left kid. If that kid doesn't exist, I first create it, and you need to do this because otherwise your try will have 10 to the 9th nodes in it. That's not okay. And finally, I insert this value into that kid. So I just keep pushing it down. This will insert something in log n time. Works fine. Okay, so what is this like? I say DP. I don't actually memorize anything because it only gets run once. But what does this DP look like? Well, there are two options. Either you can take like 1 or 0 things from your right kid and as many as you want from your left. Or you can take 1 or 0 things from your left kid, as many as you want from your right. Those are these two cases. I do these methods so I don't have to worry about null checks. I think it just makes it easier. And I also make this a static method so I don't have to worry about null checks. It's kind of the same way that I handle treats. I just think it's easier to code. All right, awesome. Very cool. So now let's talk about problem D, or problem F, if you were in div2. I thought this was an interesting problem, and I thought it was like a lot of times people complain about two versions of the same problem. I thought this was a good one because the two versions were both interesting. But we can talk about it. Yeah, so the idea behind this is that you got some array. You want to pick some continuous subarray on this array where the most frequent element is not unique. So there are two elements that both occur the most number of times. So let's think about this for a moment. In the easier version, they have this additional constraint, which is nice, which is there are at most 100 unique elements. There aren't that many different types of elements. And in the harder version, they don't have that constraint, which makes it a bit more challenging. Honestly, I think having this easier version made the harder version easier to solve for me because it put me down the right path. But anyway, now let's think about this for a minute. So one thing to notice is the only reason we couldn't take some subarray is because we have too many of some element. Let's think about it that way. Let's not think of we have too few of some element. Let's think of we have too many of whatever the biggest element is. If our subarray looks like this, maybe, and we've got like a bunch of 1s in different places. Here we've got 4 1s. Maybe we have a 3 here and here, and then a 2 here. We have too many 1s to take this whole thing. What we have to do is delete either the left endpoint or the right endpoint. Now, you can see if you look at this that the answer we're going to want is this here. That's what we're looking for. But we might not know that. But anyway, let's just say we delete the right endpoint. Okay, so we have to make it smaller. Again, we have too many 1s, we have to make it smaller. Now finally, we're at a place that works. Our last move needed to be, in order to go from a place where we have too many of something to something that works, we have to delete the most common element. In this case, we just deleted the 1, right? But we can tell ahead of time that the thing that was like causing a problem for us is going to be whatever occurs most. Because in order to make the array become valid, the only way it's going to be invalid is if we have too many 1s, if we start from the biggest amount possible. The reason for that is the number of, like the counts of each of the elements, as we delete one element, it can only change by 1. So we can't, the most common element, it can't ever be something that isn't 1 unless there was some time where it was previously valid. In order to go from having too many 1s to having too many of something else, there has to be a tie somewhere. And since we're only deleting elements, that tie would be a better answer than something after we have too many of something that isn't a 1. Okay, so hopefully I've convinced you there. The idea is that we know of these two elements that are gonna tie, we can just look at the array right from the beginning and figure out what one of those two elements is. What the other element is tricky. We don't know. It depends on how things are ordered. But one of them is definitely just going to be the most frequent element. The second example is pretty good. Let's look at it. 1, 1, 1, 1, 5, 4, 1, 3, 2, 2. So here's this. Okay. The answer for this, by the way, is there should be a 1 here. Didn't look right. The answer for this is this range here. That's what we're looking for. So what's the idea here? Well, let's say let's solve the easy problem. Let's say we brute force which of the numbers we should use as the other pair that's interesting. So we know ones are going to be interesting. In this case, let's say we brute force the other pair, we decide it's going to be a 2. So we have these numbers here. We can imagine coordinate compressing this so that we only care about the 1s and the 2s. So let's do that. I know I'm going to be kind of blocking it for a minute, but just trust me on this. It's going to be 1, 1, 1, 1, another 1, and then 2 2s. So this is what it looks like if we coordinate compress. Now, for these values here, we want to find some range where, again, the most common element, we want to find the biggest range where the most common element is like not unique. But when I say biggest, I don't just mean the most elements here, because these elements are spaced out, right? There's like a space of 2, or I guess of 3 between these two elements. There's a space of 2 between these, and there's a space of just 1 between the rest. So we want to find like the biggest space where we include that. Now, what we can do here is we can imagine instead of 1s and 2s, we've got 1s and negative 1s. So we'll keep the, whatever the most common element is, we'll make that a 1. Whatever else, like the other element that we're considering, that'll be a negative 1. Now we want the biggest range that has a sum of 0. Because if it is a sum of 0, it's got the same number of 1s and minus 1s. Now, to find that, what we can do is do prefix sums on this. It's a very common trick. So 0, 1, 2, 3, 4, 5, 4, 3. And when we do these prefix sums, we can see, okay, let's look at this 4. The range that this is valid would be this 4 all the way up to this previous 4. So this has a range of 2. And any time when we have 2 of the cumulative sum values that are the same, that indicates that the things in that range have a sum of 0. So that tells us we can safely take this range and not worry about what its sum is. Of course, if we're just looking for any 4 and we want the biggest range, then we're looking for the first 4. So we can, as we store this, we can say, all right, what's the first index of each number? When we're at some number, we just want to say, for all the stuff before us, what was the first index? And it's just going to be, that range will be the biggest range here. We have to also handle the fact that these are like coordinate compressed. So if we have this 4 here, we want this 4 and whatever is like 1 after it. And then for this 4 here, we really want whatever is 1 before this 3, right? So we would have something like this. Yeah, I think that's a sufficient answer. So let's look at the code for this, and then I'll talk about how you can do the harder version, which doesn't use that constraint. So let me clean up some of this debug really quick. All right. So I store the occurrences of every element. That's kind of boring. Don't worry about it. I convert it to integers. This part's all just kind of lame. So don't worry about that. Then I find the most frequent element. This is just whatever occurs the most. That's also pretty easy to do. There are other ways of doing this. You can do this in order 1 memory, actually, but you don't need to. So I won't talk about that. Okay, so then I brute force what the other element is going to be, and then I merge them together. I merge these two lists together in the same way you use merge sort. So I've got 2 sorted lists, and I want to merge them. And I make the deltas either -1 or +1. So in this case, I insert something from the smaller list, so I make it a -1. In this other case, I insert something from the bigger list, I make it a +1. And I store the deltas at each of these positions in the compressed list, and also what positions they map to if they weren't compressed. Okay. Yeah, so now I have this method here. I've got the positions, the deltas, and then also the size of the list. And I got to do some stuff to calculate the longest continuous range with a sum of 0. So first I calculate the smallest and the biggest the prefix sum can be. The reason for that is I don't want to use a hash map, because this is like this runs about 2 × 10⁷ times. So I didn't want to use a lot of overhead with that. I thought it would be easier to just use arrays for everything, or safer at least. And that was a good call, I think. I'm glad I did it. But what that means is, in order to avoid using negative array indices, I find the smallest this gets, and then I shift everything over by that amount. Okay, so I also store the first index of every element. The first index of 0 is just position 0, right? So if you have a cumulative sum of 0, you can end at 0. For everything else, I store what the prefix sum is. And as you see here, I update it by the delta. But before I do that, I say if you choose not to include this element, you can include everything up to this element. And that's going to be where your range ends. It ends right before this element. You also want to include everything up to the first time you had this prefix sum. So that's what this is looking at here. And then I consider that as the best possible range. Okay, and then what else? You also have to like check the end of the array. So you might go to the very end. There's nothing after that that would cause you to check it. So it's just like kind of some cleanup. Good. I think that's well explained. So now, but there's one harder part, which actually isn't that difficult to implement, but it's pretty cool, I think. The question is, now what do we do in the event that there are more than 100 unique values? So what if there are a lot of unique values? Well, here's what we can notice. Let's say we have just like a ton of ones, just like a math, like half of the array is ones. That might be a problem for us. And the reason that's the case is because we have all of these ones, right? We might have like a couple 2s sprinkled around here, 3s, 4s, maybe some 5s, and a 6 or something. Now our code actually runs in n squared because we have n over 2 unique values. And each of these times we do, like the runtime will be the number of ones plus the number of other things. But that's pretty small. So it's the number of unique values times the number of ones. And that's going to be, both of those can be about n over 2, which is a problem. That'll make our code n squared over 4, which will TLE. So in order to handle this, what we can do is we can make this a little bit smaller. Here's the observation for that. If we have just like 1, 2 in the array, and we have just like a massive amount of ones, right? We don't need to store, like if this is what our array looks like, we don't need to store all of these ones here. They're not really important. Because the sum is already just like changing so much, it's going so negative, that even if there were only 2 2s here, if there's only 1 2 in total, let's say there are 2 2s even, like this. We don't care that there are 5 ones here. Like, that's not an important thing for us to keep in mind. There might as well just be 3. So if we just have like these 3 here or whatever, then that still does a perfectly good job, because like it's not important to us that we have all of these ones here, because we're never going to be able to pick something across this range anyway. At most, we're going to be able to pick this 2 and like 2 ones across from it. So the idea is, when we build all of these ones, we're going to cut out a bunch of the ones, like maybe a lot of the ones if we only have a very small number of these other values, and we'll pay for using these ones by the other values that we use. When we do this, the total number of ones we use will be at most the number of 2s squared, right? And we'll do that for every value. So that's the idea. Here's the reason for that. Okay, let's say you've got k, more formally, you have k 2s. So you've got a 2 there, maybe you have a 2 there, and a 2 here. And then let's space the ones out equally among these. The idea is, if we take k plus 1, right? So like this part is k plus 1, this part is k plus 1. We do this for both sides of every one of these 2s. We know we haven't introduced new answers. All of the answers will be the same. And we'll be able to cut out a bunch of these things. But just by doing that, what we've done is cut the number of things that we're interested in down to the number of 2s times k plus 1 times 2, but we'll not worry about that for now. And since k is just the number of 2's, then really this is just the number of 2's squared. It's about that, anyway. Yeah, so that's the idea. We want it to like pay for things. When we do that, if we have like some element that's really big, at most it's going to use like it's really the min of this and the number of 1's. So if we have some element that's really big, we'll pay for it here. If we have some element that's small, we'll pay for it squared, right? But the worst case here, the biggest this can get, is if this is equal to the square root of n. In that case, we pay for the number of 1's every time. But we can only pay for it square root n times. That's the idea. So the total runtime here is going to be n root n. Because although we might have to pay, like the amount we pay is proportional to how big the thing is. And then it levels off at the square root of n. Okay, sounds good. Yeah, so that's my contest. Let's see, we're still pending system tests. Or are we system testing? Well, ooh, system test is almost done. Okay, I passed all except maybe this one, but we'll see. I'll end the video once I know, because I might be getting International Grandmaster today. That'd be a very good day. Can I see the div1 round, please? In Q. Well, hang on a minute. It's looking good. It's looking good. I'm very excited. Well, we'll see. Anyway, thank you guys for watching. I think I'm gonna hang out and just refresh the scoreboard, but we'll see. If it's taking like a long time, then I guess I won't. But I'd really like to know whether I got it, because that'll make me super happy. Ooh, Ericto got F. Nice job. That's solid. He's gonna skyrocket from that, I would imagine. Yeah, good job, man. It was pretty fun. I enjoyed it. Good contest. And I might be passing Square D Compton? Maybe. We'll see. It's possible. Maybe unlikely. Looks like he's gonna go up too. But good contest. All right. I'm not. I guess this is gonna be super boring to watch. I'm super excited though. Let's look at the status maybe. So we're at 156. How much time is left? Oh, it's moving pretty quick. 157. 158. Yeah, I'm gonna sit here and refresh. So yeah, thank you for watching. If you're gonna head out or skip to the end of the video, that's fine too. But I'm super excited. System tests are moving fast. Thank you, Mike. 203. What I'm really worried about is the TLE here. That's my main concern. TLE would be very scary. Also quite possible. 207. Teapot. Teapot, that's a cool name. I think I might. There you go. I'm your friend, Teapot. 209. 213. When was my submit? Hang on. It's running. Ooh, let's see it. Let's see. Wanting to test 1. Test 10. Well, we'll make it at least to 25, I hope. 16, 25, yeah, no problems there, no problems there. 30. 38. 45. 50. Looking good. Looking promising. Not getting stuck anywhere. That's what we like to see. It means no serious TLE concerns as of yet. There we go. That's very good. I think that means I just got confirmed. Well, we'll wait till it updates, but... Ooh, is plus 121 enough? It's not. I'm going to be on the border. I hope it didn't update yet. Because I think I just earned it. Yeah, look at that. 98. Yeah, so I think I just got IGM. Awesome. Awesome. That's great news. I'm super excited. I've been wanting IGM for a while. Woohoo. That's fun. Fun stuff. It's not quite a new color, right? But it's going to be pretty epic. I can't wait till this updates. Yeah, that's sick. That is, I'm super happy. Awesome. Did Monogon beat me to IGM? Not yet. He's next though. He's next on the list. Watch out. Cool. Fun contest. All right. This has been a super long video because the contest was 2.5 hours long, and I imagine it was pretty boring to watch. But hopefully, I don't know. For me, it was worth it. I'm very happy about this. It's a good contest. I did very well. I got pretty lucky seeing stuff. And it was pretty much just on the dot with performance, right? No mistakes. Just like worked out well for me. So that's, I guess when things go well, that's good. It was very fun. Cool. Well, I enjoyed. Let's see. Is it over? Are we done? It's pretty close. Yeah, I got 20 something. Maybe not 23rd, maybe 23rd. It's gonna be close. But yeah, top 30 I'm very happy with. For a div 1 round, that's pretty good. So, alright, thank you for watching. Hope you enjoyed watching the scoreboard with me, seeing whether I'd get IGM. Have a great day. Hope you enjoyed the solutions. Goodbye.